maybe there's something that you guys can take out of this. Today I'll be talking about quantum gluable states prepared through what are called sort of finite-depth local unitaries or finite-depth local unitary gates combined with quantum measurement. And so before I talk about the actual quantum side of things, I just want to go through briefly about sort of the idea of emergent phenomena. So this is interesting. I guess we have this H2O molecule here, and the physics that describes this is, what would you guys say? I mean, quantum with the electrons and everything, right? But then, so you have that one field of physics that describes just like this sort of the individual molecules. But if you take more of them, it has this like a many-body H2O molecule state, and you kind of shift to a different field of physics where now instead of quantum mechanics, you have an entirely new field of physics that describes these many-body quantum states, and that's, I guess, for example, fluid mechanics. And you have like this emergent phenomena. In this case, would be like waves, or I guess like if you had like a water ball and like it's swirling around, like you create like vortices and things like that. That wouldn't really be the case if you had just like one or two of these. But if you have a collection of many of these little parts, then you have emergent phenomena that can lead to new field of physics, new laws of physics. So that is the idea behind many-body quantum states. So instead of molecules, you can have other sorts of, I guess, micro parts of something. So you can have entangled states of matter, and they exhibit all these various types of phenomena. You could have, like, in this case, you have like spin degree of freedom spin halves on each of the sides of the lattice, and they can lead to correlations, collective fluctuations. And last week, Ryan talked about the different types of anyons, or the two-dimensional quasi-particles, and other types of particles could include Goldstone modes as well. And you also have like new phases of matter, like these exotic phases of matter. And so there's a lot of very interesting quantum phenomena that can occur during emergence. And so this is sort of the idea of investigating different types of quantum phases of matter. It's the emergence that pops out. And so this paper specifically is tackling this problem. The problem is, so we know all of these like interesting phases of weird exotic quantum phases of matter, but how do we actually realize them? How do we create them in an experimental platform in a lab? So given a platform, what entanglement patterns can I explore and realize? And so there's a practical motivation, obviously, which is that you can understand the limit of these experimental capabilities given a certain amount of tools. And they have applications for various types of quantum technologies, like one very significant example would be quantum computers or topological quantum computers. But there's also a sort of it's sort of a twofold motivation in the sense that knowing the physical properties of a many-body quantum state is quite different than knowing how to create it. And so by knowing how to create a state, that actually gives you more information about the physical properties as well. And so this is just a picture of the processor from Inflection's neutral atom quantum computer. So is there a way to, can you adjust a second? Let me see if I can. Okay, sweet. There was like the thing at the bottom. Now we don't have it, so that's good. So yes, that's sort of the main problem here.
Sorry, Rick.
Yeah.
I think you need to share your screen on Zoom.
Oh, okay. Gotcha. Thanks for letting me know. Was I not sharing earlier?
Hopefully not.
Oh my, that's my bad. Okay, cool. Now it should be shared?
Yeah.
Okay, perfect. Sweet. Okay, cool. So this is sort of the main problem that the paper is trying to tackle. And so there's this sort of like relationship between preparability of these many-body quantum states and the physical properties of these states. And so one instance of this is various physicists, such as Chen Gu-wen, they proved that long-range entangled states cannot be created by these finite-depth local unitaries. And I'll just quickly explain what I mean by long-range entangled. There's obviously sort of more formal definitions, but the idea is that if you have any kind of lattice or any kind of chain, something that's short-range entangled is you have just, I guess, a couple of entangled pairs like this. But as you move more away from these entanglements, then you sort of lose this correlation. So it's like short range entangled, as opposed to something that would be long range entangled. That would be more like this, right? It's like the entire thing is entangled. So if we know something about one qubit, or anything on this one site, then we know everything about every other qubit. So it's like long range entangled, sort of strong correlation. And so we cannot create these kind of long-ranged orders, long-ranged entangled phases of quantum matter, just using these finite-depth local unitaries, which, by the way, I'll get to right now. And it's just essentially a collection of unitary gates applied on local sites. So I can just have like something here, and this, because in this case you have like 2 qubit operations, 2 qubit unitaries. And by finite depth, what I mean by that is, let's do a few more. We have a specific constant where even as the system scales with size, this circuit stays like this. It stays with this depth here. It's finite and it stays constant. That's what I mean by finite depth local unitaries. So that's going to play a big role in a moment. But so so far we only have the finite depth local unitaries, and with just that you can't create these like long range entangled states. But if we introduce a new powerful kind of operation, which is quantum measurements, then you can actually start creating these long range entangled states. And I'll give an example in a moment. So we have these two things as sort of the experimental resources we have in digital quantum devices, and that could be like trapped ion, superconducting quantum processors, and etc. And what's really interesting about this is the fact that usually people think of quantum measurement as just like a means to an end. Once you like observe some kind of quantum state, then the wave function collapses. That's that, and that's the end of the story. But this is only the beginning. It's not the end. And he uses to create more exotic quantum phases of matter. Yeah.
I have a question. So what do you exactly mean by measurement? Does you mean you're like performing post-selection by measurement?
Yeah, so it's post-measurement. So what happens is you have a collection of all these qubits or qubit clusters. And what I'm going to demonstrate in a moment is you perform these near neighbor measurements, such as like you have a measurement here, or you have like a measurement here. And so what happens is if you perform these near neighbor measurements in a 2 qubit basis, such as the Bell basis, then through entanglement swapping, it's actually going to entangle these. It's going to entangle the near neighbor qubits, and that's going to actually lead to a new quantum state. And I'm going to give an example of that. It might sound a bit abstract at the moment, but you'll see a concrete example, and you'll be able to understand how that forms. Any other questions before I? So, I guess the idea behind this is that is there a eraser anywhere? Oh, there it is. So I'm going to give a quick analogy to this protocol. It's a deterministic protocol where you use not just the finite depth local unitaries, but you combine that with quantum measurement, and you can create these new exotic states. But what sort of the idea behind it is that, are you guys familiar with quantum teleportation? Maybe some of you guys are, right? You have like Schumann, right? You have some state that you want to send, so you have sort of like a tangled thing. But what do we do here? It's the first thing we do. We perform a measurement on these 2 qubits, and that gives us information that we can use to then act on this qubit to get back psi. So the idea is that here we apply quantum measurement, and we get sort of a classical signal, and then from that signal we have a specific protocol. We know exactly what to do, and we know like the specific type of Pauli that you want to operate on this qubit to transform it into the qubit that you want to send. So you do quantum measurement, you get information, and you have a specific protocol where you know what sort of transformation, or in our case, the finite depth local unitary that we have to operate to create the state that we're interested in. Here, we're sending a state, but in this many body quantum case, we're going to create it. And here's what I mean. And by the way, another sort of word that is used a lot is the word feedback. So you do quantum measurement, and then you get feedback, and then using the feedback, you apply the finite depth local unitaries. Does that sort of make sense? It's like it's a two-step protocol: quantum measurement, and then get information, and then you apply this finite depth local unitaries feedback. So this paper then asks the question: what kind of quantum states and I guess consequent entanglement and correlation structure can we deterministically create using measurement and feedback? And let's look at the first example here. So the first example is, are you guys familiar with the GHC state? Okay, I can talk about it real quick. It's a very interesting state. It is, you have, of course, the classic the Bell states, maximum entanglement. If you know one thing about one qubit, then you know exactly what the other qubit is going to be. So it's sort of like this idea, but now you have an arbitrary number of finite qubits, right? So this is like divided by square root 2. And I guess like suppose there's like n qubits here, and this would be the n qubit GHC state. And this is very interesting because it's also sort of known as the cat state. And the cat state is sort of the idea that, you know, you guys like heard of like Schrodinger's cats. It's like dead or alive. Those like dead and alive are very like macroscopically different sort of, I guess, states. And so is this. Like imagine having like a lattice, and everything is either up or everything is either down. It's like they differ very significantly. And so that's what we call a cat state. And the reason why we're interested in the GHC state and the cat states is because they're very easy to verify, but they're difficult to produce. So people use, I guess, the GHC state sort of as a gauge to see how well, given experimental platforms, you can create the states that you want to create. And in fact, the maximum number of qubits that has been created to create a GHC state has been just like slightly over 20. But this new protocol, this very new protocol, allows us to create GHC states of like arbitrary number of qubits. So you can have like 100 qubits instead, which is sort of insane. But this process will allow us to do that. And I guess one other thing to note here is the fact that we have these white circles. And so I guess that is covering, but that actually refers to that is referring to the time evolution unitaries. But what you'll notice is that this is the term that you should focus on here. What you'll notice is that you don't have an IT term here, and beta is actually a real number. So what you end up having is you have this, I guess, sort of unique. What do we have? This. This is sort of like equivalent to this, where H represents the Hamiltonian. And so beta is real. So what does that mean? Beta is some kind of it's a parameter for some kind of time scale, but this is real. So the time unit itself is actually is imaginary. So that's like imaginary time evolution or non-unitary time evolution, yeah.
Rohan has a question.
Oh, Rohan has a question.
Oh,
okay. And I can briefly explain why we have that. Can you just tell me the question actually?
Yeah. So Rohan is asking, isn't GHZ state preparation quasi 1D? He would have imagined that's how the leading protocols have done it. What would be new about this approach?
He said, wait, let me just check. Quasi 1D. I'm not sure what he means by quasi 1D, to be honest. Optimization. Oh, and then applying, okay. Okay, oh, I see. Here, apply how to mode. Oh, okay. interesting. Yeah, I mean this is the same idea, but it's a lot more simpler though. Like this protocol is part of the novelness comes from the fact that the imaginary time evolution allows it so that you don't have just GHZ, but you can have other forms of it, like deformed GHZ states, or other kinds of more broad many-body quantum states. Here we don't have non-unitary time evolution, and also, yeah, I mean there's no, I see. Or the deformed states in the same entanglement class? Not necessarily, I believe. I don't know the answer from the top of my head. But you'll see how this protocol is slightly different from the one that you showed here. Let's see. Okay. Yeah, I guess like another thing is here you apply this tensor product of unitaries first. Here you don't have to. It's just a two-step process. But this is interesting. Okay, thanks for your question, Rohan. Okay, this thing is like in the way. It's like.
Like make it like when you like hover over the camera, you can make it like smaller. Like where your picture is.
Oh, I can make it.
Yeah,
oh.
do that. Do that.
Yeah, that's huge. That's huge for programming. Okay. Okay. And so, I mean, we also have that this is a spontaneously symmetry breaking state, and I guess if that has any meaning to you, you can take that. But if it doesn't, the idea is that GHD states, they have a global symmetry. I'll just do this really quickly, which is that if you apply the product of x's on it, then it just stays invariant. Nothing happens. However, if you look at, I guess, one of the macroscopic states, like this is like 0, 0, 1. So this entire thing is invariant. But for some reason, when we take this, I guess, symmetry and we apply it just like for one of these, then it breaks it. Like, does that make sense? Like for the entire thing, right, the entire GHD state, you apply a bunch of x's and it stays the same. And that's because like you have x applying on all the zeros and also all the x's applying on all the ones. And this actually just gives you 1, 1 plus 0, 0, 0. So the state itself stays the same. But if you look at just one part of it, then it breaks that symmetry. And so that's what we mean by spontaneously symmetry breaking. But that's a rough idea. There's, I guess, more details into that. But I guess another way of thinking about it is if you have like a chalk or a pen, and you put it like this, you can imagine this as like sort of the GHC state. But if you knock it over like a little bit just in this direction, and it completely collapses, and now it no longer, I guess, it no longer satisfies the symmetry. Like you can collapse the wave function, it can be something like this. You can collapse the wave function, it can be something like this. For a GHC state, you would just have like zeros and ones. But for something like this, you could have like this or this or this or this or this or this or this. But these are all symmetry breaking. That's like one analogy to look at what I mean by SSP state. But if that doesn't really make sense, then you guys don't have to worry about it. It's just like one quality of this GHC state that is worth noting and part of the reason why we're interested in creating it. But anyways, this state, okay, there's a lot going on. Okay, I'm gonna just write up here. This is the goal or target. And what it is I'll just write up here. And we have this. And actually, I should explain this too. What these bonds represent is, it represents each of the qubits that are in the GHC. So you could have like 0, say 0, say 0, say 0, say 0, say, or you have like 1, 1, 1, 1, and so on. Was that a question, something? Okay. So I'm gonna check time. Okay. Does anyone else have any other questions? Okay. So this is the state that we want to prepare, and also the imagined time evolution part is not crucial. So you don't have to worry about that either. That doesn't. So this is what we want. So the preparation protocol starts with having a collection or a product state of these decoupled qubit clusters. And so like one example of the decoupled qubit clusters would just be like having 0, 0, 0, 0, 0, and so on. And this would be just like a tensor product of zeros, how many there are on the in our case, what we want is decoupled 3 qubit clusters, and actually each of these clusters is actually a GHZ state itself. And this is sort of reasonable because creating GHZ states with like a small number of qubits is fine. But then like once we start to maximize or increase the number of qubits, that's when it starts becoming hard. So the goal is we can start with this sort of easy platform, and we can achieve this state that's difficult to create using this quantum measurement and finite-depth local unitaries. So I'm gonna write this out here, and it will be helpful, I think. Let's do one more. And I guess like usually there would be n qubits, but just for clarity, I'm gonna just write 4 of these 3 qubit GHZ states. And I'll just draw qubits like this, and they all look like this. And these circles here represent this time evolution unitary. Yeah?
Might be a silly question, but are the L, C, and R just left, center, right?
Yeah, that's exactly it. Yeah, I should mention that. Actually, I'm glad you asked that because that's just somewhat important. So you'll notice like you have this unitary, this time evolution is only being applied on the center one, which is why you have just the circles on the centers of each of these GHZs. And actually, instead of writing LX, CX, and RX, I'm gonna label each of these with like 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. This is, I think, gonna be easier to see, and also I don't have to write X every time. So we have this. Does this make sense? Okay, cool. So the first step is quantum measurement. And so unlike the process that Rohan mentioned, all you do is just measurement. And what I mean by measurement here is this is relating to the question that you asked earlier, Sunbin. What you do is you perform near neighbor measurements. So I guess I'll just write down the protocol here. The first thing is near neighbor measurements. And what I mean by near neighbor measurements, I guess this is what I mean by near neighbors. This space like between the decoupled clusters. So for example, I'll do something. The sound effects are necessary, but you have like measurements, and we measure this in the Bell basis. And do people understand what I mean by Bell basis? Okay. I'll just write this real quick. And I like this notation. I'm not sure if you guys see. Instead of writing like the psi, the phi, pluses and minuses, because this is just like x applied on the 1 Bell state. This is z applied on the 0 Bell state. And this is going to be the same idea. It's going to be useful. So we do measurements on near neighbors, and the ideal situation is that we get the 1 state for all of these. We get the 1 state. That is the ideal situation. And you might be asking, why is that the ideal situation? Well, actually, do you guys want to try thinking about it? Do you guys have any ideas why we want the 1 Bell state? Okay, here's the idea. The ultimate goal of this is to connect these all together. That's really what this protocol is doing. And so what happens is if you perform near neighbor measurements in the Bell basis, so you like apply a projector, what happens is I'm gonna take this apart. Okay, this 2, 3, 4, 5. So right now, if you look at just this section, this is like 0, 0 plus 1, 1. This part here with like the 2, 3, and the 4, 5. Like these two are entangled. because they're a part of the GHZ state. So this means that if we know that 2 is in the state 0, then this is in the state 0. 4 is in state 1, this is in the state 1. But what happens is if we apply a entangling operation here, in this case the quantum measurement, we create this new entanglement like this, or actually I'll do this. If I do this, it actually breaks the previous entanglements. This sort of phenomenon is known as entanglement swapping. So you get this like new thing. And what is interesting is that if this happens to be the 1 state, this also happens to be the 1 state, i.e. this is 0, 0, 2, 5, plus 1, 1, 2, 5. And so this gets absorbed in the GHZ state, which is also like a maximally entangled state with the 0, 0, and the 1, 1s. So if we get a 1 here, then we can sort of glue these parts together. And what ends up happening is after you get the 1s, you get like I guess I'm gonna remove 2, 3, 4. Okay. So now you have this. If I look at just here, you get this new state of 4 qubits is 1, 2, 5, and 6, and that one bell state gets separated by itself like this. And so you got like 3 and 4 here. So that's the idea. So we're sort of gluing these clusters together by applying quantum measurements, which is an entangling operation. And if this idea, I guess it's like monogamy of entanglement, because it's like, let's say these are like partners, and like this person cheats with this person like this, and these guys would break up with each other and deal with that. Like you can't have like multiple like entanglements like at the same time. It's like sort of a monogamy kind of thing. So it's like sort of a swapping. But that idea allows us to sort of glue these clusters together, and that's where the term gluable comes from. But I'll give a more, I guess, concrete definition of that in a minute. But I'm gonna draw back these clusters. This is 6, this is 7. Okay. So I'll just do this here. Any questions? Yes.
Does that mean the whatever imaginary time evolution things are included in the?
Yeah, it's included in the exactly. You would have like this kind of thing, because like this, I mean, like 3 and 4 will be pulled out, and you have like 2 and 5 by themselves, but like they don't lose their imaginary time evolution terms. It just like stays. Like this, it just stays. Oh, and this is what I mean by the separation. And yeah, this is the projector in the 1 Bell basis state. So we perform. Okay, but this is the ideal situation though, and life is not perfect, unfortunately, and we get errors. And so what ends up happening is, for example, let's suppose like we get like 1 state here, we get a 1 state here. Everyone's like happy and we're like dancing, but then suddenly there's an X here. What are you gonna do? What are you gonna do? There's like a defect. And so this is where sort of the idea of feedback comes in. So we measure and we get this new information where we have this defect instead of the 1 state here. And so what we want to do is first realize that this is actually, so this can be a little bit weird or not obvious to see in the beginning. Man, I wish I had like different colored chalk. Does anyone have colored chalk by any chance? No? Okay. I guess Ryan's checking. It's fine. No. 3, 4. Oh no way. That's crazy!
That might all be broken now, but
That would be like sort of an example of spontaneous symmetry breaking. Exactly. But this is actually perfect. This is okay. Thank you so much. Okay, so we get an X state. Okay, but what is so if you think about this, like what the state exactly is, right? We have X, and it's on qubits 3 and 4. This is just a common Bell state identity is just equal to this, right? So we can. So this is a physical system, but we can express the same physical system slightly differently, where we have a 1 here, and this X gets sort of pushed out here onto the 4th qubit. Does that make sense? So you have this identity and you're doing this. Okay, that's cool. But then, so now you have X4 being applied on the GHZ state of 4, 5, and 6. Which is just 0, 0, 0.
Why is it only 4, not 3 also?
Why is it? Oh, I mean, cause like, I mean, you could have it like this, but it's the same thing. Like, I guess x3.
Oh, that should just be one of them.
Yeah, it's just one of them. And the reason, actually, I'll just write it out explicitly. Let's do 4 here. This is equal to x4 times, and I'm not going to write the normalization factors because I'm too lazy, but you have 0, 0, and then 1, 1. This is 3, 4, 3, 4. So what happens here? You have the x, Pauli x, applying on the 4th qubit. So this actually becomes 0, 1, 3, 4, plus 1, 0, 3, 4. That makes sense, right?
Okay, so
Yeah. So I essentially, like, you can describe, and actually, what you'll notice is the x, just the x Bell state. The x Bell state is literally just this. It's literally this. I mean, I guess I'm like writing the exact same thing again, but like x is 0, 1 plus 1, 0. 1 is 0, 0 plus 1, 1. This is like 0, 0, 0, minus 1, 1, and so on and so forth. And so we can express these Bell states differently by sort of pushing out a Pauli. And that allows us to push, I mean, you can have an x here, or you can have an x here. But the goal is to actually sweep all these errors all the way to the boundary, all the way to the right. And you'll see why in a moment. But this identity allows us to go from here to here. Okay, so that's the first thing. But you'll also notice this identity. Does this make sense to you guys, or do you guys want me to? Okay, let me explain it. So essentially, if you look at what a 3-qubit GHZ state would be, so if you have you have this x being applied on this thing here. So you have x Pauli x on the 4th qubit or on the 4th side, and applied here like this. Right? And this is equal to. Are you confused about something?
no.
Okay, you guys are just.
We're just thinking.
Okay. Yeah, I mean, if there's anything unclear, let me know. So this x on this qubit and this x on this qubit, it flips. It's a bit flip. So now we have 1, 0, 0, and I'm not going to make these up. That's not what that means. So you have this thing. Okay, so you have like 1, 0, 0, 0, 1, 1. You can also notice that if I have x5 and x6 being applied on the same thing,
True.
yeah, this is actually, I mean, this acts on this, and so x6 applies on this, and x5 applies on this and this qubit, and so you actually end up getting the same, state. This is the same. Let me just switch orders, right? So you have this identity, which allows us to say this. We can sort of push it to the right again. So now we have this, but then we have an x here instead and an x here instead. So we like push these errors to the right. And here's for the crucial part here. So wait, does this make sense to everyone? Okay. I'll erase this. And next slide. So yeah, so we now have this. And you might be wondering why is the x here? Well, because this Pauli x, I guess I'll just write 5. And this right here, this little circle, is e to the I, the beta x5. And the question is, does this commute or not? This commutes, right? Because this can be written as, like, if you Taylor expand it, you have this, and you have beta x plus beta x squared over 2 factorial. Tell me if I'm doing this wrong. I haven't done it.
But just because they're acting on different qubits already tells you it commutes, right?
Hmm?
It's like, oh, is this x3 or x?
This is x5. x5 and this is also x5.
Okay, yeah.
Because you have it on, they're both on the 5th qubit.
Okay.
So they commute with each other because
Yeah.
x5 commutes with each of these two. And so the fact that it commutes actually allows you to push this x through the imaginary time evolution term. So now you have like this thing. So now you have this thing at sort of the edge. And one more thing, one last thing. You notice that I mentioned earlier, if you look at, I guess this, actually I'm going to look at just this part here, you'll notice that what is going on here is you have x6 applied on this one value state, 6, 7. And this is equal to actually x7 applied on the same one value state. This makes sense? Okay. So because of this, you can push it again to the right, so you get this thing instead. So now, essentially, what we started out was we had a defect here, and we sort of pushed it to the right, except we have another one at the physical boundary. But this is we can take care of this with the finite-depth local unitary feedback. And so you just do this again. You have this on the left side. This becomes this. So you have x here and x here, but this disappears. So you have x here, and this becomes x here, and so this becomes. Like, you get the idea, right? You can keep on pushing these things, like, to the right. And ultimately, what you end up having is you have this sort of, this situation where you have x, 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 and then you have, I guess, another x here. I mean, if this was the boundary, then this can't really go anywhere else because it's at the boundary. So you have an x here, and then you have an x here. So this is what you end up with. And so, yeah.
So it seems like if it hits another Pauli X measurement, then
Exactly.
it deletes. But then,
Yeah.
but then all the time evolved ones past it won't have the X on it.
Yeah, exactly.
It's only everything in between. has
Yeah,
it.
that's exactly it. Yeah, we apply. So if I just go here, we apply this tensor product unitary feedback, or the finite-depth local unitary feedback, where you have this non-local string that you precisely described. So if I drew like a line, I mean, this is just a string of Paulis, right? You apply these, and so because x squared is the identity, these, actually, I'll just erase these. These disappear, these disappear, these disappear, these disappear. And also, I forgot to these are all now connected because of the near neighbor measurements. Because like once we have the one, then we can pull out the state and then we can glue these clusters together. Does that make sense? Okay. So yeah, so we can correct these errors using a non-local string. And we're saying non-local because the error originally sort of appeared here, but we're sort of applying on the right of it. But physically, there's no difference with the pushing. This is just like, I guess, a different diagrammatic representation of the same physical state. And so, if I did not draw any of those, like, these x's, what you can sort of imagine is, if I just had an x here, right? And I apply this, non-local string of Paulis, right? If I just apply this onto each of these center qubits, then what you end up getting is this thing. Get a bigger GHC, where you have like 1, and then I guess 3 and 4 disappear, 2, and then I guess right. So you get this GHC state, which is precisely what we wanted. Yeah.
What happens if you have more than one errors?
Yeah, if you have more than one error, then actually, suppose we have like something like Z instead. If we had something like Z instead, so we had Z. What is interesting about Z is the fact that, I guess by the same virtue of being able to push the X out, you can push Z out. So you have a Z here. But the thing with Z is that Z applied on, I'll just go back to this arbitrary notation with this being on the left qubit. This actually equals the same thing as applying on the right qubits. And this is just an identity that you can check yourself, and it's nice because it's a GHC state, so you can push this Z from the left to the right. So you just like push, Z is like literally getting pushed to the right. And so when you have multiple errors, you just do the same push, like sweeping operation, I guess like one at a time, until you have like a bunch of these. And you have like you could have like a Z here, Z here, Z here, Z here, X, Z. And so you would first apply a bunch of X Paulis, so these would all cancel out. and then you would apply a string of z, or actually not even a string. You just have to apply, because the thing is, you don't get z's like this. Everything, the z just gets pushed all the way, so it just becomes like this, which is why. So for x's, you have like this non-local string, but for z's, you can actually just push everything to the right like this, and then now you just have one z at the end, and then so you just apply the z at the boundary, and these cancel. So that's what you have. That's what you do when you get, I guess, multiple errors or different errors. And so these errors are sort of known as topological errors, and they relate to actually defects in, I guess, a specific type of quantum phase of matter called symmetry protected topological phases. Which I don't know if I have the time to actually. What time is it? 2:47. Okay, we can talk about that another time. So this is the idea. This is the idea of gluing these clusters together. And so we have these things called gluable quantum states, and we just, the definition, sort of an informal definition. We say that a one-dimensional many-body quantum state is gluable if they're deterministically comparable with the following ingredients, which was you have this product state of this entangled clusters, and then you apply near neighbor measurements in a complete 2-qubit basis, and then you apply the tensor unitary feedback, or the finite-depth local unitaries. And you just need a finite amount of them, since there's a finite number of qubits, so you can only have a finite number of errors. And so it's like taking decoupled clusters, which are then glued together with these single round of, it's a single round, it's really nice, it's one physical action. Actually, like the measurement is one physical action, and applying the physical, and this is all like a physical action, like you would do something like in the lab to do this, but you have one measurement and then just one physical unitary feedback, and then you're done. And so you get this interesting GHZ state. And of course, it's not only GHZ, you can do this with the aforementioned like SPTs, symmetry protected topological orders, or you can do it with like trivial states or product states, and there's a lot of things that you can do. And this extends not only for 1 dimensions, but also 2 dimensions with like PEPs, but that becomes a little bit more complicated. And so what this paper did was it established a relationship between how a state is prepared using measurement and sort of the physical properties, I guess more specifically correlation lengths, entanglement spectrum, and so sort of the phase of matter. And I guess I don't have like a lot, I guess, yeah. The idea of like correlation lengths or I guess entanglement spectrum just talks about how much are their states like entangled. Like for example, are they short range entangled or are they long range entangled? Like what is sort of the correlation? Like if we know something about 1 qubit, then how much do we know about the rest of the qubits? That's sort of like the correlation entanglement spectrum concepts or the properties. And so we have this first theorem. So the paper has all these like theorems, and they have this entire classification of these one-dimensional quantum gluable states. The first theorem says that non-local correction constrains the entanglement spectrum, and so the non-local correction that I was talking earlier was this, because you apply this tensor unitary feedback not on where the error was, but pretty much like on the right side of it. So when you apply this, then you get well, it says if a wave function is preparable by gluing and all measurement errors require non-local correction, then its entanglement spectrum is constrained to be flat. Essentially what that means is that you have a long-range entangled state, which in this case, an example of that is this, precisely this. So this is sort of like an example of that theorem. And another theorem would be like local correction, so like having to correct things on like locally, like here. Constrains correlations, so it goes, if a wave function is preparable by gluing, there's just a measurement error that can be locally corrected, then there exists an operator with 0 correlation length. And the idea of correlation is that, this, this. So we have like this finite-depth local unitary. The fact that we have correlation means that, as I said earlier, if you know one thing about 1 qubit, then you can know what, I guess, the near qubit, like the other qubits that are near that 1 qubit are going to behave. But 0 correlation length means that after you go a certain finite distance, like it goes like, imagine a light cone, it goes like to here. So after you pass this point, then you know nothing about the other qubits. So it's like it's sort of restrictive per se. But that's the idea of correlation length. And if you guys want to talk about it after, I can talk about it for sure. So the conclusion of the paper is that it demonstrated how and when quantum measurement can create many-body quantum states. and it presents sort of a large landscape of preparable states with the classification of the 1D states. And it establishes various rigorous theorems distilling the power of quantum measurements, at least for specifically the one-dimensional case. And yeah, thank you for your attention. Yeah.
This seems doable if you just have a bunch of 2-qubit GHZ states. What's the point of the third qubit, and why are you time evolving it?
Yeah,
That didn't
the
seem
time
to-
evolution thing, I don't know. Like, I can't. If you were to ask me to like derive it mathematically, I wouldn't be able to do that. But the point of the time evolution is that if you have just like regular, just like unitary evolution, then you don't get sort of like these exotic properties such as like non-zero correlation length, or these different types of entanglement spectrums. It's like these sort of more exotic imaginary time evolution that allows for these kind of properties to arise. And the question with the 2-qubit thing is just, I guess like the physicist and the author tried thinking about it, but I mean, I guess I feel like I reckon there might be some kind of issue. Oh yeah, I guess like if you have an error here.
Oh, if you have two errors next to each
Yeah,
other.
you have two errors next to each other, and they would conflict with one another. Yeah. Yeah. Any other questions?
Yeah, just like obviously this is only for 1D, and like, do you think like this is something that could be generalized to like higher dimensions, and
Yeah.
then also like experimentally, like let's say you wanted, like you know how like you can put like the Z, and it creates like edge state defects. Like if let's say like you actually wanted like the edge state defects, you think you could like actually do that in like
Yeah.
experimentally.
That's like what's in the frontier right now.
Yeah,
People are
yeah,
investigating
that's
theories. But there's also some things that people are not sure about the 1D case. Is like, for example, like here we worked in the Bell basis, but like to what effect does this play a role with the possibility of being able to do this? And actually, the idea comes from like quantum error correction, but like this is sort of a specific example of what's called an error basis. And I mean, I guess you can sort of tell with the different error defects we had. The errors are described in this specific error basis, but you can have like generalized forms of error bases. And the paper talks about like if you have like unitary, so like all the operators in the error bases are all unitary. There's also something called a nice error basis, which is I guess another form of a generalization of these Bell basis states. But they have this sort of special mathematical concept sort of equipped to them, the idea of like projective representations. And so that idea is involved in proving a lot of these theorems that are explained in the paper. But one thing that has not been explored is what if you have something that is not an error basis? And that's called a wicked error basis. It's called wicked. That's the name. So actually, my research project is exploring what types of quantum phases of matter would arise from wicked error bases. That's like what I'm working on right now. And this is like, I don't know, this is an interesting question. But it's just literally anything that's not a nice error basis. So you could have like sort of like wicked quantum physics of matter, which would be interesting. And I don't know whether they would lead to SPTs or topological order, or maybe new phase of quantum matter. That would be really interesting. Yeah. Oh yeah, you had a question? Something?
Yes. How many syndrome measurements like you have to perform to like glue the states together?
I guess that depends on the size of the system that you want to create, but it would just be a finite number.
Finite number.
Yeah, it would be a finite number. Right. There's nothing else I have in mind to add to that. But yeah, finite number.
Saw a figure early in the presentation where it seemed like there were several layers of these like.
Oh, the finite-depth focal interface. Yeah, that's just like an illustration of what they are.
Oh, okay.
Yeah, I guess like.
Another question: what year is this from?
This is from
Is it from like this year? Or
It's
or
from,
last
like,
year, last year?
the late end of last year.
Really?
Yeah.
Wait, how did it take so long to like? Why did it take so?
It's just like, I guess part of it is
Why
sort of a new new perspective of looking at things, like looking at physical properties by thinking about how we can prepare these, like sort of from like a resource theoretic perspective.
okay.
Sort of more a novel idea, or people haven't explored it as much compared to other ideas. But like part of it was inspired from like all the new like quantum technological advancements we have, with like I mean you can ask Shivin, he's an expert, but with like the tweezer arrays, I forgot what they were called exactly, but like that like those kind of things inspired the physicists Ruben Versen and Rahul. I gotta credit the others. Yes. Oh yeah, Rahul Sahay, Ruben Versen. So Rahul's a PhD student at Harvard, and Ruben's PME assistant professor. So yeah. Yeah.
How difficult would it be to selectively evolve only the middle qubit of those?
Oh no. I mean, I would imagine like it wouldn't be a difficult thing, which is why they decided to attach these imaginary time evolution terms. It's just like the point of, I mean, I guess like physically there's not really much of a difference between unitary and non-unitary or imaginary. It's just like the math that describes it leads to these exotic properties. But I wouldn't imagine that it would be hard experimentally, at least. That's what I would think.
It would depend on the
Right.
experimental platform, right? Like,
Yeah.
it would, like, I don't think it would be any like specific, like you're only targeting the middle. It's like it'll be the same if you targeted the left or right. It would just be
Yeah.
the error rate of like state selectively involving one thing. So in atom tweezers, you would like normally like detune the selected atoms and then only evolve those in the unitary to make them resonant with the laser. So whatever error rate is associated with that, and whatever error rate is associated with the unitary in your experimental system, that'll be those will be the errors.
For sure. Yeah.
So what was the method they used to prepare these states before this paper?
I mean, they didn't really have a method before. I mean, the thing is like.
No, like what was used like before that? Before what's been used in the past few years?
There's the idea of using quantum measurements to do actual quantum computations, but the idea of like preparing quantum states is sort of a more newer thing. So that idea wasn't really like explored back in earlier times. But I guess Rohan did point out that this process itself is not a novel thing. Like people have discussed this like just a couple of years ago, but I guess what's new about this paper specifically is it classifies like discretely like what types of quantum phases of matter can arise. Like it describes like every single possibility. It describes an entire classification. And it turns out these states can be all represented into something called a matrix product state. And they would talk about the relationship between the matrix product states and what kind of symmetries you have on the system and what kind of quantum phases of matter consequently come out of those two combinations or other combinations as well. But yeah.
So I think his questions was how did they prepare GHG states experimentally before this one, I guess. Is that your question?
Yeah, I think so.
People just
Well, that's
brute
part of
force with
They
Just
use
series, right?
adiabatic state preparations in like neutral atom platforms. Like you start with the transferism of a Hamiltonian, and you can tune the parameters from the ZIZJ, which is basically means the nearest neighborhood coupling of the Z operators, plus plus the HX operators. So you have a nearest neighborhood coupling part and a single qubit excitation part. So you tune the parameters between the two adiabatically, then you can prepare the GHD states from the product states.
Okay.
But you have to do that slowly because it's adiabatic process. So that's how they prepare, and I believe the one you use, I guess you in your presentation you said that they have prepared GHD states up to 20 qubits. I guess
That's the maximum
Yeah.
number, or like a little bit over 20.
Yeah, that 20 qubit was come from I guess that state adiabatic state preparation.
Yeah, and I guess like that raises an interesting point, which is that, as I mentioned before about the resource theory perspective. This takes a lot less resources than like the version that Rohan showed or the version that you showed. There's a lot more unitaries that you need to apply to create the GHC state as opposed to this, which is just like a couple strings and then you just need one I guess round, one round of quantum measurements. Which is nice. It's also kind of interesting because like quantum measurements are a non-unitary process. So it's like you're sort of combining non-unitary and unitary processes together, and that can lead to like these interesting exotic phases.
Now I have like one more question.
Yeah.
To measure like quantum states in the Bell basis, you have to first perform the Hadamard transformation, and you have to then perform CNOM to like couple of the states together.
Yeah.
For basically just transit from the computational basis to the Bell basis, you have to perform CNOM operations, and that will also propagate the errors even more. So I guess that will create like more errors, like multiple X and Z errors. So I'm just wondering whether this method is robust even under those circumstances.
Yeah, I guess that's an interesting point because they didn't really talk about the fact that you had to apply the Hadamard or the
CNOMs.
CNOMs to the Bell basis.
You cannot just measure Bell states with just computational basis. Like of course you can do it, but you have to do it like exponentially many times. For you to do like just with a single shot, you have to like transform the basis.
Yeah. That's a good point. I wonder if like the imaginary time evolution terms play a role in that. I can't really think of how they would, but maybe. But with the process that you described, you just have, isn't it just a process of just like zeros? 0, 0, 0, 0, 0, and then you do the Hadamards and the CMOS. You don't start with already existing GHC states or JC like clusters.
Yeah, obviously you will start with
Like 0, 0, 0, 0, 0, 0, 0.
3.
Or no?
Basically.
Yeah, but that's like slightly different than, well, I guess like we already have these like small entangled clusters, and I think because of the fact that they're already entangled allows us to perform these spell measurements.
And 3 GHCs usually.
Yeah, like the 3-qubit GHCs. I mean that's right. Like if I like because you have like the GHC states, you have already this. I guess you would be able to describe the fact that because you have these 3-qubit clusters like in the GHC states, you can describe the whole system in terms of the Bell basis instead of like a single qubit basis. So you would be able to
I guess just for concreteness, like you don't need to do the computation, but would you know how to set up the measurement computation of the like 3 and 4?
Yeah. Do you mean like mathematics?
Yeah.
Okay. Yeah.
Just a setup of it. You don't need to solve it.
Yeah. Sure.
We compute how it would look.
Right. So suppose you have like, we have this. Let's do this real quick. So you have. I have Hogger and chalk. I have like a whole tin. I'll be sure. And I think earlier what happened when you like dropped the box, it didn't seem like anything like cracked, but I think a lot of the chalk actually did. Weird. Sorry. But I have like extra chalk, so yeah, I'll get some. But anyways, you have GHC. I'll just draw this for clearly. Well, what Shivan is asking is, from here you're just looking at, I guess, this section. And what you can sort of do is, this is, I guess, we'll just call this like the initial state. And I guess just to make it easier, we'll call these like 1, 2, 3, 4. And so, right now, currently, these are entangled. These are entangled. So another way to write this is we have this is equal to the Bell basis 1, 2 times this. Right. But what happens is as you perform a measurement, so you apply a projector onto the 1 state for 2 and 3. So you have 2, 3, and 2, 3. You apply this on here, and it turns out that more like using wire tensors or tensor network implementation. These get so you have like actually so this this bra here. I'll do this. This bra here, the blue connects these, and this ket here. This ket green is like down here. And this is actually this becomes this. You have 1, 4, and you have 2, 3. So you have this thing. So what happens now is that these get removed, these get connected, and then you have a separate like 1 state. 3, 4. This would be this section would be this. And this is so much simpler than actually writing this entire thing out. Which I mean, if you want me to, I can write it out for you.
Yeah, I'm good, but
Okay.
but yeah, no, I just wanted to see that. Okay, cool, thank you.
Yeah. I mean, I guess yeah, it's a mess.
So you don't care about the leftmost and the rightmost at all, right? They're not
Yeah.
part of the network. Okay.
Yeah, right. I mean, because you're not performing measurements on them, so
Yeah.
the entanglement swapping doesn't like affect them.
Okay.
Yeah.
Cool.
Yeah.
But I guess that only works for the one state, the 0, 0, plus 1, 1.
Oh no, actually, that's a good question. What happens is, suppose you. Oh, this is actually really interesting. Suppose you decide to, instead of applying the 1, let's say you applied like x. What do you think happens? Like I'll just say, I mean, around x here. So these were previously in the 1 state.
So it goes
But it
X
turns
state.
out this becomes an x state as well.
So they're both X states.
Yeah.
Okay.
You get x. It's good.
Oh
But
yeah,
I-
they're not orthogonal then? Oh yeah, because you're working in a more macroscopic space, but you're only applying like a sub-orthogonal part.
Yeah, exactly. It's projection onto the substance.
Yeah, okay.
And I think, I mean, now that I look at this is only possible because you have these clustered qubits. These clusters of entangled, small clusters of entangled qubits. If you had like the setup where you had like 0, 0, 0, 0, 0, 0, 0, 0, like this would not be possible. This would not be possible, and you would have to apply like Hadamard and CNOT.
Yeah,
Um,
they are not entangled,
yeah, they're not entangled, right? It's products.
obviously.
Yeah. This is nice because like these 3 qubit clusters are not that hard to realize. But yeah, see it.
Might be looking at the wrong thing, but I found this one paper that says like they have a Bell state measurement at 62.5% accuracy. Like, wait, is that the right number? Or?
I'm not sure what that. I mean, you could have defects like from the quantum measurement, but I'm not sure what it means by 62.5%. I mean, I could say that I'm not an experimentalist, so I don't know what that means, but like, I guess I'm not sure. I'm not sure what that means. Wait, actually, can I see?
Yeah. I'm guessing like, if it's this low, what are they improving on? I'll show you.
Wait, what is the number?
Sorry?
What's the error rate or what you said?
Success probability of 62.5%.
Of Bell-state projection circle. Oh, okay. Oh, current Bell-state measurement schemes. Oh, I mean, so they're using optics here. Only 2 of the 4 Bell states can be identified. I see. Okay. So I guess like the Bell basis measurements. Here, just demonstrate. Yeah. So I see what you mean. Achieve success probability. Oh, okay. I mean, this apparently it's an improvement from before. They're more able to accurately perform these Bell state projections or the Bell basis measurements. But I guess this is a good point. And maybe like this protocol with the finite-depth local unitaries and the quantum measurement, maybe it would involve some sort of a different experimental platform instead of optics. It could be lasers or anyons or how much. I mean, it comes. But yeah.
So that error is pretty bad though, right?
Yeah.
Yeah, I mean like that.
Yeah, I mean, it's
Research,
improvement, but
research.
it's like, yeah.
Wait, so like,
We're
isn't
getting
this
there.
supposed to be experimentally minded though? Like
This one?
creating this?
Is that the implementation? No. Is this paper you're reading the implementation?
No.
Yeah, that's a.
There's just some
Pepper,
random
right?
one.
Yeah.
This paper is just all theory.
Yeah.
Oh, okay.
Yeah, it's all.
It's like
Do you guys want? I mean, I can show you what the paper actually looks like because it's a long paper. So they have like deformed cluster state, and this is a symmetry protected topological state. It's like you can like, and you have like deformed trivial. And so you have like the theorems that I mentioned earlier. But say like that's like one part of the thing. They have more theorems. Then they have like a general setup of formalism. They have a more rigorous definition of like these global quantum states. And then this is describing the process, but in terms of the matrix product states here. This is just like all the annotations, like, and then they're talking. Then they do a lot of these proofs using the tensor network notation, and so they like describe that, and then you have like a lot of these things, and then okay, cool, blah blah blah, topological errors, which I mentioned briefly, and then can keep on going. Oh my, oh okay, now it's done. Psych, there's like even more. But this is like really interesting stuff. And actually, this is I'll go to the error basis thing. Somewhere, meshes. Sample errors. Oh my god. Oh yeah, error basis. Error basis. So they sort of generalize the idea from go basis to error basis, and then they prove that these are nice, and the nice error basis also happen to be unitary error basis. But yeah, that's the paper. So if you guys want to take a look at the proofs with me sometime, if you guys are interested, let me know. So I would be down. Yeah. Yep. Thank you so much for your attention.
Yeah, let's thank Rick again.